manood na sa teleradyo. Makinig, manood na sa teleradyo. Teleradyo, teleradyo Marcelo. Sa gitna ng mapanubok na panahon, magkahatid sa kakibat ay diskusyon. Sama-sama tayo, kahit magkalayo. Sa programang ito, tiyak ang pagkatuto. Teleradyo, teleradyo Marcelo. Teleradyo, teleradyo Marcelo. Teleradyo, teleradyo Marcelo. Makinig, manood na sa teleradyo. Makinig, manood na sa teleradyo. Teleradyo, teleradyo Marcelo. Sa gitna ng mapanubok na panahon, magkahatid sa kakibat ay diskusyon. Sama-sama tayo.
Hi, good afternoon. I am Engineer Roel A. Damdam, or you can simply call me IRAD, your physical science teacher here at Teleradyo Marcelo, ang telearalan ng bawat Dalpalarian. First, I would like to acknowledge our secondary school principal for Dr. Maria Victoria C. Vivo. Good afternoon po, ma'am. And my master teachers, Maurosita A. Lopre and Sir Bartolome R. Asa. Magandang hapon po. And to my senior high school faculty, and to all the grade 11 students tuning in with us here at Teleradyo Marcelo. Okay, so today, we are going to talk about the formation of heavier elements in the universe. Here are our objectives. By the end of the session, you should be able to first analyze the formation of elements during that 3 nucleosynthesis, and then identify the different elements formed in each nucleosynthesis. And then third, explain how the concept of atomic number led to the synthesis of new elements, and finally analyze the nuclear reactions involved in the synthesis of new elements. In your chemistry class, you learned what elements are, and an element is a pure substance that cannot be broken down by chemical means. And to refresh your memory, let us have this activity. You are going to arrange these jumbled letters, flash on the screen, to form the name of an element. We will start first with the elements that are found in the Earth's atmosphere. Let us start with the first one. So, what do you think is the answer? Okay, that is correct. Nitrogen is our first element. Okay, for the second element, here are the jumbled letters. What do you think is the name of our second element? Okay, very good. Oxygen is the other element found in the Earth's atmosphere. So for the third element, arrange the jumbled letters now. What elements can you see or can you form from the letters? Okay, good job. Argon is the answer. So the Earth's atmosphere is actually composed of about 78% nitrogen, 21% oxygen, 0.9% argon, and 0.1% other gases. All matter is made up of elements. and they are also present in the human body, in other living things and non-living things, and in celestial bodies. So where did these elements come from, and how did they come into existence? Let us now proceed to what happened 14 billion years ago. There was a tremendous explosion that occurred, and this explosion started the expansion of the universe. What do you call this explosion? Okay, you are correct. The explosion is known as the Big Bang, and so the universe began with a bang. And this Big Bang theory has something to do with the formation of light elements. Let me discuss how these elements were formed during the process known as Big Bang nucleosynthesis. We cannot imagine how hot and dense the universe was after the Big Bang. When the universe was just 10 raised to negative 34th power second old, it experienced an inflation, which is an incredible burst of expansion. The expansion was so great and faster than the speed of light. During this time, the universe doubled in size at least 90 times. And after inflation, the universe still expanded, but at a slower rate. And as space expanded, the universe cooled and the matter formed. And 1 second after the Big Bang, the universe was filled with protons, neutrons, electrons, anti-electrons, photons, and neutrinos. Okay, so during the first 3 minutes of the universe, the light elements were born during Big Bang nucleosynthesis. And the temperature of the universe cooled down from 100 nonillion Kelvin to 1 billion Kelvin. And this collision of protons and neutrons took place, and deuterium, an isotope of hydrogen, was formed. Most of the deuterium combined to helium or to make helium, and trace amounts of lithium were also produced. So heavy elements were not formed during the Big Bang nucleosynthesis. Now the question is, where did they come from? Okay, so after Big Bang, most of the elements in the universe were produced by the stars in the nuclear fusion reaction at its core. The process is known as the stellar nucleosynthesis. It is the creation of heavy elements by nuclear fusion reactions within the stars. It has occurred since the original creation of hydrogen, helium, and lithium during still the Big Bang time. The Earth and all other heavenly bodies are believed to be remnants of the star. In our case, we are considered part of the debris of a big star in its active existence. Now, what happens during nuclear fusion inside the star? The stars are made mostly of hydrogen and helium. So these elements are packed so densely in a star. The pressure in the center of the star is so great, and this is enough to begin nuclear fusion reaction. The question now is, what is a nuclear fusion reaction? So nuclear fusion is the process by which two or more atomic nuclei join together to form a single heavier nucleus and large amounts of energy. So most commonly, in the core of a star, the two hydrogen atoms fuse to become a helium atom. Although nuclear fusion reactions require a lot of energy to get started, but once they are going, they produce enormous amounts of energy. So when most of the hydrogen is a core, the star begins to die out. So this dying star expands into a red giant. The star now begins to manufacture carbon atoms by fusing 3 helium atoms as its core. Rarely, a fourth helium atom combines to produce oxygen. So stars of about sun's mass stop within burning stage and collapse into white dwarfs about the size of the Earth. Okay, so there is a relationship between the mass of the star and the formation of heavy elements. The higher the mass of the star, the heavier elements it can create in its core. The reason behind this is that the heavy element fusion requires higher temperatures, which can only be achieved by massive stars. So after all this, the hydrogen in the core has been changed to helium. Massive stars begin a series of nuclear burning, such as carbon burning, neon burning, oxygen burning, and silicon burning. So carbon undergoes fusion reactions to produce oxygen, neon, sodium, and magnesium. So throughout the neon burning stage, this neon fuses into oxygen and magnesium. And during the oxygen burning stage, oxygen forms silicon and other elements that lie between magnesium and sulfur. Okay, as you can see on the screen, the high massive stars can make all elements up to and including iron in their cores. So the heaviest element that stars can make is iron. When fusion of iron occurs, it does not create energy. Without the supply of energy, the star will soon die. So now let us proceed to supernova nucleosynthesis. Okay, so more massive stars become super red giant, and when their core runs out of fusion fuel, the core collapses and resists gravity. Then the star is doomed. As gravity squash the core, the star expands and it explodes and releases tremendous amount of energy. The explosion is called a supernova. When the supernova explosion happens, dying stars undergoes a rapid capture of massive number of neutrons under extreme temperature. This rapid neutron capture converts elements into heavy isotopes and decays into heavy elements. So after we discuss how light and heavy elements were formed, let us now go to the synthesis of new elements. So if you want to know some information about an element, you can bring your periodic table or you can search online a copy of a periodic table. So the arrangement of elements in the periodic table underwent several modifications. This periodic table had several gaps in the 18th century. So these gaps were reserved for unknown elements. Scientists were not able to solve the puzzle in the periodic table, despite all the attempts to fill the gap. It was English scientist Henry Moseley who realized the atomic number is another property that supports periodicity. So take note that Mendeleev's periodic table was organized according to atomic mass. But the atomic number represents the number of protons in the nucleus of the atom. And it was used to determine the order of the elements in the periodic table. Okay, so the modern periodic table contains the elements that are arranged in increasing atomic number based on the mathematical relationship between atomic number and X-ray frequency. Because of this development, the mystery of the missing element was solved. And all the gaps in the periodic table were finally filled in with a new system of order in the periodic table, which was based on the atomic numbers of the elements. So, synthetic elements, as you can see on your screen, these are naturally occurring elements, and there are also synthetic elements. So, synthetic elements are radioactive elements that were not discovered occurring in nature, but they are artificially produced isotopes. So in other words, they are man-made. So consider the first lightest element ever synthesized, technetium. This element was discovered in 1937 by Carlo Perrier, and Emilio Segre. The name was derived from the Greek word teknetos, which means artificial. Technetium has an atomic number of 43. It fills the gap between elements 42 and 44. It was the first element to be produced artificially. This element was found in a sample of molybdenum. The molybdenum atoms were bombarded with deuterons that had been accelerated by a cyclotron. Okay, so we also have this element called transuranium elements. So these elements are elements with an atomic number greater than 92, which is an atomic number of uranium. So all of these elements are unstable and decay radioactively into other elements. So these elements are artificially generated. They are synthetic elements which are produced using nuclear reactors or particle accelerators. So currently, scientists are searching for element 119 or element 119. So if you have a way, please make a way for finding what can be produced for element 119 or element 119. So we have talked about nuclear fusion earlier. There is also another process known as nuclear fission. So this one, it is a process in which the nucleus of an atom splits into two or more smaller nuclei, and usually some byproduct particles. So, in other words, nuclear fission is a form of elemental transmutation, or moreover, emission of radiation is more apparent in nuclear fission since particles tend to be radioactive and further they decay. Okay, so atoms may undergo any of these three radioactive decay processes. As you can see on your screen, it is the alpha decay, the beta decay, and then the gamma decay. So transmutation of these elements is best expressed with the use of nuclear equation. You can see in the nuclear equation on the screen the atomic mass and the atomic number or nuclear charge of the parent and daughter nucleus. So regardless of the type of radioactive decay, the atomic mass and the nuclear charge are conserved on the left and right side of the nuclear equation. So let us first have the alpha decay. So alpha decay is a type of radioactive decay in which the atomic nucleus emits an alpha particle, which is helium nucleus, and it transforms into another atomic nucleus. So in this type of decay, the mass of daughter nucleus decreases by 4 and its charge decreases by 2. Let us have an example. As for example, we have uranium-238. So uranium-238, when it undergoes alpha decay, it transmutes into an atom of thorium and gives off alpha particle. Okay, so that's what happens when it undergoes alpha decay. So next we have a process of beta decay. Beta decay is another type of radioactive decay in which the parent nucleus emits high energy electrons. Either it could be beta positive or it could be beta negative particle. So in this case, the mass of daughter nucleus remains the same, but daughter nucleus will form different element. So let's have an example for beta. So you can see that the nuclear equation shown on your screen happens to be carbon-14. So carbon-14, when it emits beta negative particle, it transmutes into atom of nitrogen-14. okay, with a nuclear charge of 7. So that's what happens for process of beta decay. So lastly, we have a type of radioactive decay, which is the gamma decay. So what's kind of radioactive decay this one? So when an atomic nucleus undergoes gamma decay, no particles are ejected from the nucleus. So instead, high energy uh, form of electromagnetic radiation, which is a gamma ray photon with no charge, is released. So as can be seen, if an atomic nucleus undergoes a gamma decay, the atomic mass and nuclear charge of the daughter nucleus remain the same. So take note that the daughter nucleus will form different energy state of the same element. So that is why there is a superscript M to indicate that the parent and daughter nuclides are nuclear isomers, which means that they are the same isotope but in a different energy state. Okay, so we have an example for gamma decay, which is the technetium. So technetium 235, when it undergoes gamma decay, gamma ray is emitted. Okay, so now let's have an exercise. Can you identify the daughter nucleus when thorium-230 undergoes alpha decay? Okay, very good. So the answer is radium with an atomic number of 88. Okay, let's have the next one. Okay, what is the element formed when thorium-234 undergoes beta decay? Okay, what you are thinking is correct. The answer is proctaxinum with an atomic number of 91. So at this time, let us have now this assessment. I will be reading questions and the choices and say the letter of the correct answer down. Say the letter of the correct answer and let's check if you are correct or incorrect. Okay, for number 1. Which of the following elements was produced during the Big Bang nucleosynthesis? A. Helium, B. Iron, C. Oxygen, or D. Uranium? Again, which of the following elements was produced during the Big Bang nucleosynthesis? A. Helium, B. Iron, C. Magnesium, or D. Uranium? Okay, the correct answer for number 1 is letter A, helium. So you got it right. So for the next problem, please keep on answering and assess yourself if you are getting the correct answer. Okay, for second problem, what is the heaviest elements that the high massive stars can produce? We have A, oxygen, B, carbon, C, iron, or D, magnesium. Again, what is the heaviest element that the high massive stars can produce? A, oxygen, B, carbon, C, iron, or D, magnesium? Yes, the correct answer is letter C, iron. So iron is the heaviest element that the high massive stars can produce. Okay, for the third item, we have what is the first element that was synthesized? A. Technetium. B. Purium. C. Fermium. Or D. Nobelium. Again, what is the first element that was synthesized? A. Technetium. B. Purium. C. Fermium. Or D. Nobelium. Correct. The correct answer for this particular item is letter A, technetium. So technetium is the first element that was synthesized. Okay, down to the last two problem. We have number 4. So question for number 4 is, what type of radioactive decay does not change the nuclear charge? Is it letter A, alpha decay, B, beta decay, C, gamma decay, or D, all forms of radioactive decay affect the nuclear charge? Again, what type of radioactive decay does not change the nuclear charge? Letter A, alpha decay, B, beta decay, C, gamma decay, or D, all forms of radioactive decay affect the nuclear charge. Okay, so the correct answer for this is you are correct with your answer, which is letter C, gamma decay. So gamma decay is the type of radioactive decay that does not change the nuclear charge. Okay, for the last item. So question is, what happens to the atomic mass and nuclear charge of the daughter nucleus in an alpha decay? Is it letter A, the atomic mass decreases by 2 and the nuclear charge increases by 4? Or letter B, the atomic mass decreases by 4 and the nuclear charge increases by 2? Or letter C, the atomic mass decreases by 4 and the nuclear charge decreases by 2? Or letter D, the atomic mass and the nuclear charge remain the same? Okay, the question again is, what happens to the atomic mass and nuclear charge of the daughter nucleus in an alpha decay? Letter A, the atomic mass decreases by 2 and the nuclear charge increases by 4. Letter B, the atomic mass decreases by 4 and the nuclear charge increases by 2. Letter C, the atomic mass increases by 4 and the nuclear charge decreases by 2. Or letter D, the atomic mass and the nuclear charge remain the same. So what is your answer? Okay, very good. So the correct answer for this particular item is letter C. The atomic mass decreases by 4 and the nuclear charge decreases by 2. Okay, so if you think you got at least 4 over 5 of this assessment, I think you're doing good with this topic. So for others who have a poor remark, do you have any questions? If you have, please don't hesitate to put your comments or to personally message me or any of our science teachers that are handling physical science subject. And if none, I would like to introduce to you the members of the production team. Okay, so yours truly, Irad, your teacher broadcaster for today. My script writer, Ma'am Joy May Bulaong, and our technical director, Ma'am Josephine Nicolas. And of course, I would like to thank the whole Teleradio team Teleradyo Marcelo team for this opportunity for us to broadcast this particular topic. Okay, so lastly, I would also like to share to you with this, before we end, I would like to share to you this quotation. So the quotation here says that there are as many atoms in a single molecule of your DNA as there are stars in a typical galaxy. And so each of us is a little universe. So thank you and God bless.
Makinig, manood, nasa teleradyo. Makinig, manood, nasa teleradyo. Teleradyo, Teleradyo Marcelo. Sa gitna ng mapanubok na panahon, magkahatid sa kaakibat ay diskusyon. Sama-sama tayo, kahit magkalayo. Sa programang ito, tiyak ang pagkatuto. Teleradyo, Teleradyo Marcelo. Teleradyo, Teleradyo Marcelo. Teleradyo, Teleradyo Marcelo.